Hello students, welcome all of you. In this video, I Abhay Kumar going to discuss a very important topic in waves and acoustics, which is forced vibration for B.Sc Part 1 Physics courses, that is Physics Honors, Physics Subsidiary and Physics General. In lecture number 5, first of all, we have to define forced vibration. When a body capable of vibration vibrates or oscillates under the action of an external periodic force, it is called forced vibration. जब कोई बॉडी किसी एक्सटर्नल पीरियोडिक फोर्स के एक्शन में के प्रभाव में वाइब्रेशन करता है अपने इक्विलिब्रियम पोजीशन के अबाउट, तो इसे फोर्स्ड वाइब्रेशन कहा जाता है. नाउ वी हैव टू ऑब्टेन द डिफरेंशियल इक्वेशन ऑफ मोशन ऑफ द फोर्स्ड vibration and then its solution, and in last we will obtain the condition of amplitude resonance in case of forced vibration. But first of all, we have to obtain the differential equation of motion of the forced vibration. For it, suppose a body vibrating about an equilibrium position under an external periodic force which is given by capital F0, that is F naught sin Pt, sin a small p into t, that is a sin p, F0 sin Pt. Let x be the displacement of the body from its equilibrium position at any instant, and dx by dt its instantaneous velocity during the vibration. Suppose किया जाए कि कोई बॉडी किसी एक्सटर्नल पीरियोडिक फोर्स जिसे रिप्रेजेंट किया जाता है एफ नॉट, कैपिटल एफ नॉट साइन पी टी, तो इसके एक्शन में बॉडी ओसिलेट करता है अपने इक्विलिब्रियम पोजीशन, दैट इज पोजीशन ऑफ रेस्ट ऑफ द बॉडी. एंड सपोज किया जाए कि एक्स, स्मॉल एक्स, किसी टाइम टी पर, किसी इंस्टेंट टी पर उस पार्टिकल, उस बॉडी का और पार्टिकल का डिस्प्लेसमेंट है फ्रॉम द इक्विलिब्रियम पोजीशन, दैट इज पोजीशन ऑफ रेस्ट ऑफ द पार्टिकल ऑब्लिक बॉडी. एंड उस टाइम टी पर उस बॉडी का इंस्टेंटेनियस वेलोसिटी, दैट इज रेट ऑफ चेंज ऑफ डिस्प्लेसमेंट dx अपॉन dt है. देन इन केस ऑफ फोर्स्ड वाइब्रेशन, थ्री फोर्सेस विल कमिंग इन टू प्ले. फोर्स्ड वाइब्रेशन के केस में थ्री फोर्सेस पॉसिबल हैं जो कि क्रियाशील होंगे उस बॉडी पर एक्ट करेंगे. फर्स्ट फोर्स इज रीस्टोरिंग फोर्स विच इज प्रोपोर्शनल टू द डिस्प्लेसमेंट ऑफ द बॉडी फ्रॉम द इक्विलिब्रियम पोजीशन, फ्रॉम इट्स इक्विलिब्रियम पोजीशन, and it is given by restoring force is equal to minus k into x. Since restoring force is proportional to displacement of the body, so restoring force can be written as restoring force equals to minus k into x, where k is a constant of proportionality which is called force constant. So restoring force acting on the body during the oscillation or during the vibration is given by minus k into x, where k is a constant of proportionality which is called force constant. And the restoring force negative sign indicates that the restoring force opposes the displacement of the body from its equilibrium position. Negative sign यह indicate करता है कि restoring force बॉडी का उसके इक्विलिब्रियम पोजीशन से, पोजीशन ऑफ रेस्ट से डिस्प्लेसमेंट का अपोज करेगा. सो हेयर इट इज माइनस साइन. This is the first force, restoring force acting on the body, which is equal to minus k into x. Second force is frictional force. or damping force, frictional force, that is due to frictional force is the opposing force due to medium, that is due to presence of medium. तो मीडियम के कारण, दैट इज फॉर एग्जांपल एयर रेजिस्टेंस, तो इसके कारण जो फोर्स बॉडी पर एक्ट करेगा, अपोजिंग फोर्स मीडियम के प्रेजेंस के कारण, मीडियम बॉडी के मोशन में मीडियम बॉडी के मोशन को ऑब्स्ट्रक्ट करेगा, दैट इज फ्रिक्शनल फोर्स एक्टिंग ऑन द बॉडी विच इज फॉर एग्जांपल एयर रेजिस्टेंस. सो फ्रिक्शनल फोर्स is proportional to instantaneous velocity of the body, that is dx by dt, and therefore frictional force can be represented by minus some constant, say constant b multiplied by dx upon dt, where b is another positive constant, that is a constant of proportionality. So frictional force due to presence of medium or due to presence of medium acts on the body during the vibration or motion of the body, and it also opposes the motion of the body, and frictional force is given by minus b into dx upon dt. dx by dt is the instantaneous velocity of the body. And third force is an external periodic force applied on the body, and under the action of which the body oscillates. फोर्स्ड ऑसिलेशन में बॉडी अप्लाइड पीरियोडिक फोर्स के फ्रीक्वेंसी से, दैट इज अप्लाइड फोर्स के इन्फ्लुएंस में ऑसिलेशन करता है, वाइब्रेशन करता है. देयरफॉर दैट एक्सटर्नल पीरियोडिक फोर्स इज गिवन बाय, एंड थर्ड फोर्स इज एन एक्सटर्नल periodic force, say it is F naught sin PT, where capital F naught is the maximum value of the applied force, and P, a small p, is the frequency. A small p is the angular frequency of the applied force. So these three forces coming into play during the forced vibration of a body. First is a restoring force, it is given by minus kx. Second is frictional force due to air resistance, that is due to presence of medium, due to obstruction of the medium, and it is given by minus b into dx by dt. And third force is an external periodic force, बाहर से बॉडी पर अप्लाई किया गया पीरियोडिक फोर्स, आवर्ती बल, जिसके कारण बॉडी वाइब्रेट कर रहा है फोर्स्ड वाइब्रेशन के केस में. तो थर्ड फोर्स इज F नॉट साइन PT. सो टोटल फोर्स एक्टिंग ऑन द बॉडी इज गिवन बाई F इक्वल्स टू माइनस kx माइनस b dx by dt. नेगेटिव साइन है, नेगेटिव साइन indicates that both forces, that is the restoring force and frictional force, opposes the motion of the body. So total force acting on the body is capital F is equal to net force acting on the body, or total force acting on the body, capital F is equal to minus kx minus b into dx by dt plus F naught sin PT, and suppose it is equation number 1. Now using Newton's second law of motion, total force acting on the body, F is equal to mass into acceleration. Suppose a small m be the mass of the body or particle which is vibrating under an external periodic force, which is given by F0 sin PT. Using Newton's second law of motion, LHS of equation 1, that is net force capital F, we can write it as a small m into d square x by dt square, because force is equal to mass into acceleration. Hence we have a small m into d square x upon dt square m is the mass of the body or particle, and RHS is minus, RHS is, since RHS is minus kx minus b dx by dt plus f naught sin pt. So taking both negative terms of RHS into LHS, we have m into d square x upon dt square plus b dx by dt plus kx equals to f0 sin pt. Both negative terms, taking both negative terms, that is minus kx and minus b dx by dt into LHS, we have m into d square x by dt square, which is total force acting on the body using Newton's second law of motion, plus b dx by dt plus kx is equal to f naught sin pt. Now dividing both sides by m, we have first term becomes d square x upon dt square plus b by m. Second term becomes b by m dx upon dt. फर्स्ट टर्म में m से डिवाइड करने पर m से m कैंसिल हो जाएगा, प्लस थर्ड टर्म इज के एक्स, सो इट इज k बाई m इंटू एक्स इजकल टू f नॉट, RHS becomes f naught sin pt upon m, that is f naught upon a small m sin pt. Here f0 is the maximum value of the applied periodic force. बाहर से जो periodic force आवर्ती बल अप्लाई किया गया है उसका मैक्सिमम वैल्यू f नॉट है, और इस इक्वेशन का इक्वेशन 2 सपोज किया जाए, इट इज इक्वेशन एबव इक्वेशन इज इक्वेशन 2. तो डिवाइडिंग इक्वेशन 2 बोथ साइड्स बाई स्मॉल m, दैट इज मास ऑफ द बॉडी, वी हैव डी स्क्वायर एक्स बाई डी टी स्क्वायर प्लस बी बाई एम डी एक्स अपॉन डी टी प्लस के बाई एम एक्स इक्वल्स टू f0 कैपिटल f0 अपॉन m, दैट इज मैक्सिमम फोर्स अपॉन मास, दैट इज force upon mass is acceleration, so it can be written as capital F naught upon small m can be written as f0, which is the acceleration of the body, into sin pt. P is the small p is the angular frequency of the applied external force. Now b by m, b is a small b is a constant, that is constant of proportionality, that is damping constant, upon m is mass of the body, which is also constant. So b upon m is another constant. B upon m will also constant, and it can be written as, say it is 2r, and k by m, k is force constant upon mass. Mass of the body is also, mass of a particular body is also constant. So k by m is another constant, is also constant. K by m is also a constant, and say it is omega square. So this equation becomes, or d square x upon dt square plus 2r, in place of b by m, say it is 2r, a constant, 2r into dx upon dt plus k by m is also a constant. So it is, say it is omega square x equals to f naught, maximum value of the applied external periodic force upon mass, that is it is f0, a small f0, that is acceleration, force upon mass is acceleration of the body, f0 sin pt, and say it is equation number 3. So this is the differential equation. This is the differential equation of the motion of forced vibration. Now we have to find its solution. So this is the differential equation, which is given by equation 3, that is d square x by dt square plus 2r dx upon dt plus omega square x is equal to f naught, a small f naught sin pt, and this is the differential equation of forced vibration. It is differential, write down, equation of the motion of forced vibration, or differential equation of the forced vibration, Now let us try its solution. Let x is equal to a sin pt minus theta will be its solution. So the solution of this differential equation of forced oscillation is the solution of the differential equation of the forced vibration is x equals to capital A sin pt minus theta, and suppose it is equation number 4. Now differentiating both sides of equation 4, that is the solution of the differential equation given by equation 3, that is d square x by dt square plus 2r dx upon dt plus omega square x is equal to f naught sin pt. In place of b by small m, we have written 2 small r, that is r is the damping constant, 2r term is damping constant, that is b by m. Now differentiating equation 4 twice, we will obtain the values of dx by dt and then d square x by dt square. So after first differentiation, that is differentiating equation 4 with respect to time, we have write down differentiating equation 4 both sides with respect to time twice, equation 4 both sides twice with respect to time t. We have first time it is dx by dt, which is instantaneous velocity, dx by dt is equal to a is constant, so a times sin pt minus theta is cos pt minus theta multiplied by, now theta is constant, so differentiation of pt minus theta is constant, so it is p into dt by dt, so it is only p, so we have a into p, ap cos pt minus theta. So dx by dt is after differentiating 4 with respect to time, so first time it is dx by dt, it is ap cos pt minus theta, and let it is equation number 5, and then after then in second differentiation we have d by dt of dx by dt, again differentiating it, that is equation 5 with respect to time, we have d by dt of dx by dt, that is d square x upon dt square equals to ap, which is constant, and differentiation of cos pt minus theta is minus sin pt small p t minus theta, and then differentiation of pt minus theta is constant, so it is p into dt by dt, so it is p only and it becomes now ap into p, that is ap square minus ap square, and differentiation of cos pt minus theta is minus sin pt minus theta, so it is minus ap square sin pt minus theta, say it is equation number 6. So we have obtained the values of dx by dt, d square x by dt square, and also x, which is the solution of this differential equation given by equation 3. Now substituting the values of d square x by dt square, dx by dt, and x in LHS of equation 3, that is differential equation of the forced vibration, we will we get, or we have, so we have write down d square x by dt square is minus, in LHS of equation 3 we can write, hence equation 3 becomes d square x by dt square is minus ap square sin pt minus theta, and now in second term, it is second term of differential equation of forced vibration given by equation 3, is 2r plus dx by 2r multiplied by dx by dt. dx by dt is the instantaneous velocity. dx by dt बॉडी का जो कि फोर्स्ड वाइब्रेशन में ओसिलेट कर रहा है अपने इक्विलिब्रियम पोजीशन के अबाउट, तो dx by dt उसका इंस्टेंटेनियस वेलोसिटी है किसी टाइम, किसी इंस्टेंट टी पर, किसी टाइम टी पर. सो इट इज 2r एंड dx by dt इज वी हैव ऑब्टेन्ड इट ap cos pt minus theta in equation 5. So it is 2r into ap cos pt minus theta, and the third term is omega square. Third term of the differential equation given by 3 is omega square x. So it is omega square multiplied by x. X is the solution of the differential equation, given differential equation of the forced vibration, which is x is equal to a sin pt minus theta. So it is a sin pt minus under bracket pt minus theta, and RHS is f0 f naught, a small f0 or a small f naught sin pt. Sin pt can be written as sin pt minus theta under bracket. Sin pt can be written as sin pt minus theta under bracket plus theta. So result will be sin pt minus theta plus theta, minus theta and plus theta will cancel out, and then the result will be only f0 sin pt. But by writing this we can use the formula sin a plus b, that is sin a into cos b plus cos a into sin b. तो ट्रिग्नोमेट्री का फॉर्मूला यूज करने के लिए, जिससे कि LHS एंड RHS दोनों साइड में pt माइनस थीटा के कोफिशिएंट को इक्वेट किया जा सके, इसलिए RHS को हमने लिखा f0 साइन अंडर ब्रैकेट pt माइनस थीटा प्लस थीटा. सो वी हैव नाउ LHS इज और माइनस LHS is minus AP square sin pt minus theta, and third term is omega square is sin pt minus theta. So we can taking a common in first and third term, we can write minus omega square minus omega square minus omega square under bracket omega square. थर्ड टर्म को वी कैन राइट थर्ड टर्म फर्स्ट. थर्ड टर्म इज पॉजिटिव, सो वी कैन राइट थर्ड टर्म फर्स्ट एंड देन फर्स्ट टर्म फॉलोड बाय दिस टर्म. सो इट इज ओमेगा स्क्वायर. थर्ड टर्म को पहले लिखा जाए, पॉजिटिव है, उसके बाद फर्स्ट टर्म को. सो ओमेगा स्क्वायर ए विल बी कॉमन, ए कॉमन होगा बोथ टर्म्स में, फर्स्ट टर्म एंड थर्ड टर्म में. सो वी कैन राइट ओमेगा स्क्वायर माइनस पी स्क्वायर इंटू ए को बाहर कर लिया जाए, कॉमन है दोनों में, सिंस ए इज को कैपिटल ए इज कॉमन विच इज द एम्पलीट्यूड. तो ए ओमेगा स्क्वायर माइनस पी स्क्वायर एंड इट इज साइन पी टी माइनस थीटा. बोथ टर्म्स में पी टी माइनस थीटा है, तो ये भी कॉमन होगा, साइन पी टी माइनस थीटा. सो वी हैव ए अंडर ब्रैकेट ओमेगा स्क्वायर माइनस पी स्क्वायर ब्रैकेट क्लोज साइन पी टी माइनस थीटा प्लस 2r ए पी कॉस पी टी माइनस थीटा, and now it is RHS is f0 sin pt minus theta plus theta. So f0 sin pt minus theta into cos theta plus a small f0 cos sin a plus b is equal to sin a into cos b plus cos a into sin b plus f0 cos pt minus theta multiplied by sin theta. Now suppose it is equation number 7. Now equating coefficients of sin pt minus theta and cos pt minus theta in both sides of this equation, that is equation number 7. We have write down equating the coefficients of sin pt minus theta and cos pt minus theta in both sides of equation 7. इक्वेशन 7 के दोनों साइड्स में साइन पी टी माइनस थीटा एंड कॉस पी टी माइनस थीटा के कोफिशिएंट को इक्वेट किया जाए। तो राइट डाउन इक्वेटिंग द coefficients of sin pt minus theta and cos pt minus theta in both sides of equation 7, we get in LHS coefficient of sin pt minus theta is a, capital A under bracket omega square minus p square, and in RHS coefficient of sin pt minus theta is f0, f naught cos theta, small f0, small f naught cos theta. So we have a into omega square minus p square will equal to coefficient of sin pt minus theta in first term of RHS of equation 7 is f0 cos theta. So it is f0 cos theta, suppose it is equation number 8, and coefficient of cos pt minus theta in second term of equation in LHS of second term of equation 7 is coefficient of cos pt minus theta is 2rap. So 2rap इक्वेशन 7 में के LHS के सेकेंड टर्म में cos pt माइनस थीटा का कोफिशिएंट 2 स्मॉल r ap है। सो 2rap एंड RHS में cos pt माइनस थीटा का कोफिशिएंट है f0 sin थीटा। So coefficient of cos pt minus theta in RHS of equation 7 is f0 sin theta. So 2rap is equal to f0 sin theta, and it is equation number 9. Now to get the value of the resultant amplitude A, squaring and adding equation 8 and 9, we will obtain the value of amplitude, that is maximum displacement of the force vibration. So a squaring and adding equations 8 and 9, we have a squaring. Now after squaring and adding equations 8 and 9, equations 8 and 9 को both sides में स्क्वायर करके ऐड कर दिया जाए. So we have a square, LHS is a square multiplied by omega square minus p square whole square plus 2rap square, that is 4 small r square, a square capital A square into p square, and RHS is f0 square small f0 square cos square theta plus f0 square sin square theta. So f0 will be common in both terms. So f0 square cos square theta plus sin square theta, and cos square theta plus sin square theta is 1. So in RHS it is only f0 square. So we have f0 square. So we have a square in LHS is a square omega square minus p square plus 4r square a square p square is equal to f0 square. So taking a square common in LHS, we have a square, that is amplitude square, a square is taken out of the bracket, a square को bracket को बाहर कर लिया जाए. So it is a square under bracket omega square minus p square plus 4r square p square equals to f0 square. It is a small f naught square. So a square will be f0 square upon omega square minus p square plus 4r square p square. Now we have capital A square, that is amplitude square equals to a small f0 square upon under bracket omega square minus p square का whole square plus 4r square p square bracket closed. Therefore amplitude capital A equals to root under a square root of a small f0 square upon omega square minus p square to the whole square plus 4 square, 4r square, small r square, p square. So a square root of f naught square in the numerator is f naught only, upon in the denominator it is root under a square root of under bracket omega square minus p square whole square plus 4r square p square, and it is equation number 10, and it is the expression for amplitude in case of forced vibration. Amplitude of forced vibration, amplitude of motion in forced vibration of a body is capital A is equal to f naught, a small f naught upon root under omega square minus p square whole square plus 4r square, a small p square. Since a square is equal to f naught square upon omega square minus p square whole square plus 4r square p square. Therefore, amplitude A becomes, capital A becomes root under f naught square upon omega square minus p square whole square plus 4r square p square. So, we will get, we have already obtained capital A amplitude of forced vibration is capital A is equal to f naught upon root under omega square minus p square whole square plus 4r square p square. Now, we have to obtain the condition of amplitude resonance, but before it we have to substitute this value of amplitude capital A is equal to a small f naught upon root under omega square minus p square whole square plus 4r square p square in equation 4, that is solution of the differential equation of forced vibration given by equation 3. So, substituting the value of amplitude capital A in equation 4, which was the solution of the differential equation of the forced vibration given by equation 3. So, we get equation, hence equation 3 becomes x equals to capital A, value of capital A is f naught upon root under omega square minus p square whole square plus 4r square p square into sine pt minus theta. The value of theta we will also obtain by dividing f naught sine theta upon f naught cos theta, that is in terms of tan theta. By dividing previous two equations we have already obtained. So, x is equal to f naught upon root under omega square minus p square whole square plus 4r square p square into sine pt minus theta, and it is the solution of, it is the final solution of the differential equation we have obtained in equation 3. We have obtained in equation 3 of the forced vibration, x is equal to, a small x is equal to f naught upon root under omega square minus p square whole square plus 4r square p square sine pt minus theta. This is the final solution of the differential equation of the forced vibration, and value of sine theta we will value of theta we will obtain by dividing two equations we have already obtained in this topic, that is f naught cos theta is equal to a capital A under bracket omega square minus p square, and f naught sin theta is equal to 2 RAP. So, dividing f naught sin theta upon f naught cos theta, we will get the value of tan theta, and from and then value of theta. So, we can write tan theta, where theta we will obtain will be tan theta f naught sin theta by f naught cos theta equals to 2 RAP upon a r square omega square minus p square. A and a will cancel out in the numerator and denominator. So, it will be 2 RP upon omega square minus p square. This is the value of tan theta, and from it we obtain the value of theta, that is tan inverse 2 RP upon omega square minus p square. Now we have to obtain the condition of amplitude resonance in case of forced vibration. The amplitude of forced vibration will be maximum if the denominator of this solution x is equal to f naught upon root under omega square minus p square whole square plus 4 r square p square sin pt minus theta. This is the solution, and amplitude expression for amplitude is a is equal to f naught upon root under omega square minus p square whole square plus 4 r square p square. So amplitude will be maximum if the denominator of equation 10 which we have substituted in equation number 4 also, that is in the solution of forced differential equation of the forced vibration. So for amplitude to be maximum, we have denominator of equation 10 should be minimum. So now write down for amplitude resonance condition of, we will obtain the condition of amplitude resonance, that is for maximum amplitude, the denominator of equation. Write down for the maximum amplitude, that is the body will vibrate with maximum amplitude. बॉडी फोर्स वाइब्रेशन के केस में बॉडी मैक्सिमम एम्पलीट्यूड के साथ जब वाइब्रेट करेगा तो उसके लिए एम्पलीट्यूड का वैल्यू मैक्सिमम होना चाहिए. तो फॉर मैक्सिमम एम्पलीट्यूड कैपिटल ए, द डिनोमिनेटर इन इक्वेशन 10 शुड बी मिनिमम, दैट इज टर्म ओमेगा स्क्वायर माइनस पी स्क्वायर होल स्क्वायर प्लस 4 आर स्क्वायर पी स्क्वायर अंडर ब्रैकेट अंडर स्क्वायर रूट शुड बी minimum, then amplitude will be, amplitude of force vibration will be maximum. So for the maximum amplitude in equation 10, for the maximum amplitude in equation 10, the denominator of equation 10 should be minimum, that is, and we know that for maxima and minima dy by dx is equal to 0. So therefore we have d by dp of the term containing in the square root of the denominator, the term inside the square root of denominator in equation 10, that is in the expression for amplitude a is equal to f naught, a small f naught upon root under omega square minus p square whole square plus 4r square p square. तो डिनोमिनेटर अगर इस इक्वेशन 10 का में इक्वेशन 10 जो एम्पलीट्यूड के लिए एक्सप्रेशन है फोर्स ऑसिलेशन के केस में, तो एम्पलीट्यूड फोर्स ऑसिलेशन का के केस में एम्पलीट्यूड मैक्सिमम होगा जब डिनोमिनेटर मिनिमम होगा. और फॉर मैक्सिमा मिनिमा वी नो दैट dy by dx इक्वल टू, अप्लाइंग द कंडीशन ऑफ मैक्सिमा मिनिमा, dy by dx इक्वल टू 0. सो इन दिस केस d by dp ऑफ omega square, the term inside the square bracket, the term inside the denominator, the term inside the square root present in the denominator, स्क्वायर रूट के अंदर जो टर्म प्रेजेंट है उसका डिफरेंशिएशन पी के रिस्पेक्ट में क्या होगा, 0. सो बिकॉज द टर्म शुड बी टर्म इन द डिनोमिनेटर, that is omega square minus p square whole square plus 4r square p square should be minimum for maximum amplitude A. So we have d by dp of under bracket omega square minus p square whole square plus 4r square p square equals to 0. Now differentiating both terms, that is first term omega square minus p square का whole square, that is omega square minus p square to the whole square plus 4 and then 4r square p square with respect to p, and then equating and RHS is 0. So we have now differentiation of first term inside the bracket with respect to p. P is the angular frequency of the applied periodic force. So we have differentiating first term, it is omega square minus p square का whole square है, पावर फंक्शन है. So it is 2 omega square minus p square 2 minus 1, that is 2 minus 1 is power, 2 minus 1 is 1 using the differentiation formula. So it is only 2 p square omega, differentiation of omega square minus p square omega square, that is first term inside the bracket with respect to p is 2 omega square, 2 under bracket omega square minus p square, 2 minus 1, that is 2 omega square minus p square, and then differentiating now with respect to p, the term inside the bracket omega square minus p square, that is omega is constant in this case because differentiation is with respect to p, so it is 0. Differentiation d by dp of omega square is 0 minus second term inside the bracket is p square, so differentiation of p square with respect to p is 2p plus 4r square, second term is 4r square multiplied by p square is 2p, differentiation of p square is 2p and RHS is 0, or we have minus 2p, 0 minus 2p in first term in of LHS, it is 0 minus 2p minus 2p into 2 that is minus 2 into 2 multiplied by minus 2p, that is minus 4p under bracket omega square minus p square plus 4r square, that is 4 into 2 8r square p is equal to 0. Now taking the first term, that is negative term in RHS of this equation, we have 8r square p equals to 4p omega square minus p square, and 8 will cancel out in LHS by 4, that is 2, p and p will cancel out, so it is 2r square equals to omega square minus p square. 2r square is equal to omega square minus p square, therefore p square, that is a square of the angular frequency of the applied periodic force, it is p square, it is omega square minus 2r square, and suppose it is equation number 12. If damping is small, then the term containing the term 2r square, damping term, r is damping constant, 2r we have already taken in place of b by m, a small b by m, we have already taken 2r. So if damping is small, then r small r is equal to 0. So neglecting 2r square, the term 2r square, so since r becomes 0, if damping is a small r equals to 0, that is 2r square equals to 0, r is equal to 0, nearly equal to 0. So neglecting 2r square in equation 12, it is equation 12 becomes, we have p square is equal to omega square, that is p is equal to omega, that is the angular frequency of the applied force, periodic force, must be equal to the natural frequency of the oscillating body, and this is the condition of amplitude resonance. If the angular frequency of the applied periodic force is becomes equal to the natural frequency of the oscillating body, then in that case the amplitude of forced oscillation will be maximum, and it is called amplitude resonance, and it is the condition, a small p is equal to omega is the condition of amplitude resonance. It is the condition of, write down in last, it is the condition of amplitude resonance in case of forced vibration. Now this video is completed. यदि यह वीडियो आप सभी को पसंद आया हो तो इस वीडियो को अधिक से अधिक लाइक करें तथा मेरे यूट्यूब चैनल फिजिक्स क्वांटम क्लासेस को भी अधिक से अधिक सब्सक्राइब करें. थैंक्स ऑल ऑफ यू फॉर वाचिंग माय यूट्यूब चैनल फिजिक्स क्वांटम क्लासेस.